Hello everyone, my name is Lau Jia, a final year electrical and electronic engineering student from University of Nottingham, Malaysia. My final year project title is Non-Volatile Flip-Flop for Low Power Application. The main goal of this project is to design a memristor-based non-volatile flip-flop at circuit level for low power application. So, flip-flop is the fundamental circuit component of all sequential logic because it enables memory-based logic operations. Flip-flops are found everywhere in digital circuits. A D flip-flop is a type of flip-flop with only one input, D. So why do we need a non-volatile D flip-flop, right? So the mainstream method of low-power IC design is through transistor downscaling and threshold voltage reduction. However, as technology node becomes smaller, the effect of leakage current, such as subthreshold leakage, becomes more prominent due to the small size of transistor. Therefore, another popular method in low-power design is to unpower subcircuits of system-on-chip (SoC), such as the slim mode operations commonly found in wireless sensor network application. However, conventional flip-flops are made of transistors, which are volatile. Complete power down is impossible in a flip-flop when data retention is required. Other than planned power down, unpredicted power down is another scenario to consider in low-power circuit design, such as in the energy harvesting application. So this motivates the integration of non-volatile memory into the design of flip-flops, which leads to the terminology of non-volatile flip-flop, NVFF. Memristor is a highly potential non-volatile memory technology candidate with high memory density and also fast read and write speed. In 1971, the mathematical model of a memristor was first proposed by Professor Leon Chua as the fourth fundamental two-terminal circuit element, alongside with resistor, inductor, and capacitor, due to its unique electrical property where resistance changes based on the history of current flow through the device. However, it was until 2008 where the first practical memristor model was fabricated by HP Lab. The working principle of a memristor can be simplified as follows. When voltage is greater than the positive threshold V set is applied to the device, the memristor will be switched to low resistance state, also known as R-on. When negative voltage with magnitude greater than negative threshold V reset is applied to the memristor will switch to high resistance state, also called R-off. The difference between R-on and R-off is several orders of magnitude. Therefore, a memristor can be used to store binary values reliably. Ideally, the memristor state remains non-volatile when disconnected from power. With this memory property, memristor can be used in the design of non-volatile flip-flop. In this project, a memristor with 0.161 volt threshold is used. Now, let's take a look at the conventional way of designing a flip-flop. A D-latch is a device that can change its output logic based on input when it is enabled, and it remains the same logic indefinitely, despite there's a change in the input if it is not enabled. So one conventional method to design a D flip-flop is to cascade two D latches in master-slave configuration. The master is connected to the clock bar signal while the slave is connected to the clock signal for a rising edge flip-flop. By cascading the latches in master-slave configuration, output logic that is clock edge triggered can be observed as shown in this timing diagram here. Therefore, this type of configuration works as a flip-flop. As shown in the following figures, right? Conventional CMOS transistor D flip-flops are designed by cascading CMOS D-latch in master-slave configuration. In this project, two types of conventional D flip-flops are used to benchmark the other designs. So as shown here, namely conventional D flip-flop and also conventional transmission gate D flip-flop. One is using pass transistor as switch and the other one is using transmission gate as the switch. Across the literature, there are two general design patterns for a non-volatile D flip-flop. In design pattern number 1, as shown here, memristor is connected to the latch in master-slave flip-flop as a backup unit. In design pattern number 2, memristor is used as the latch itself inside a master-slave flip-flop. Using this design pattern, data will be read from memristor continuously using the read voltage which is below the memristor threshold when the latch is non-transparent. However, continuous reading may cause the memristor state to be modified, as not all memristor exhibit ideal threshold characteristic. Therefore, design pattern number 2 was not used in this project. In this project, 2 types of non-volatile D-latch are designed, and then 4 types of non-volatile D flip-flops are designed by cascading different D-latch in master-slave configuration. The first proposed D-latch is called Read and Restore Non-Volatile D-latch, RRNVDL. The term read and restore represents the ability of this design to restore memristor state after reading. The read and restore operation allows read voltage greater than the memristor threshold value. Note that the range of the read voltage is limited to be greater than myristor threshold and smaller than VDD minus the threshold. So when the clock is high, right, the latch will be transparent. The path of current flow is highlighted in green color, as shown in this figure. Right? The input D is connected to point VQ, and therefore is also connected to output Q. That's why it's called transparent mode. The voltage difference that exists across the myristor due to the complementary value of the D input will cause the change in the myristor stage. So for example, as shown in this figure, if D is equal to 1, the myristor will be switched to low resistance state because a positive bias voltage will exist across the myristor. When the clock is low, the latch is non-transparent, meaning the input D is isolated from the circuit, as shown here. Again, the path of current flow is highlighted in green color. So under this non-transparent mode, read voltage VSS will be applied across the myristor. If the myristor state is low resistance initially, let's say, then the voltage at point Q, VQ, will be close to the read voltage VSS. Inverter 1 will interpret VSS as logic height and outputs at 0, and therefore inverter 4 will output at 1. The node VQ is finally reinforced at logic 1 VDD level by inverter 4. The voltage difference between the final VQ and VSS restore the state of myristor after reading it. And due to the back-to-back connected inverter 1 and 4, the output Q is latched at the previous logic value. Due to this read and restore ability, the design allows read voltage VSS that is greater than the threshold of myristor without modifying the state of myristor after reading. RR and VDL discussed earlier can be cascaded in master-slave configuration to form a non-volatile D flip-flop named as RR and VDFF MS1. By using non-volatile D latch in master-slave configuration such as RR and VDFF MS1 mentioned just now, the constructed non-volatile D flip-flop should be able to restore logic 1 or 0 during restoration of power supply, where the power is cut off prior. This image shows the typical power restore operation of a non-volatile D flip-flop. When the circuit is powered down at 40 microseconds, the myristor will retain the output logic state. When it is powered back on, the clock will initialize at low cycle, and then the non-volatile D flip-flop will restore the logic by reading from the myristor. Another type of D latch is designed based on RR and VDL by changing pass transistor within the design to transmission gate. It is named as RRTG and VDL. Then, another D flip-flop, non-volatile D flip-flop, is designed by cascading two RRTG and VDL, and it is named as RRTG and VDFF MS1. Next, another non-volatile D flip-flop is also designed by cascading conventional D latch CVDL with RR and VDL in master-slave configuration, and it is named as RR and VDFF MS2. Note that this design is named as MS2 master-slave configuration 2 because the master and slave latch are different. One of them is volatile and the other one is non-volatile. That's why it's named like this. Finally, okay, another non-volatile D flip-flop design is constructed by cascading CVTGDL with RRTG and VDL, and it is named as RRTG and VDFF MS2. So all the proposed designs are simulated in LT-SPICE for different transistor gate length technology, which are 22, 32, and 45 nanometers, using predictive technology model from Arizona State University. The transistor length follows the gate length technology, while the transistor width are adjusted for circuit performance, which is not detailed in this presentation. Different voltage levels are used for this design when different transistors is used because the transistor parameters are different. The following table summarizes the voltage levels of input and output port used, where lower voltage is used for smaller transistor. Through LT-SPICE simulation, all the non-volatile D flip-flop designs are verified to be able to operate under power restore operation. The following figure here shows an example of the simulation result using RTG and VDFF MS2 in 45 nanometer transistor model. Next, the propagation delay analysis was also carried out for the designs. Propagation delay is calculated as the average of low to high and high to low clock to Q delay of the D latch and also the flip-flop. Based on the result, two observations are made. Number one, designs using transmission gate generally have lower delay compared to design using pass transistor. This is because transmission gate effectively reduces the voltage loss during passing of logic level. And then in number two, in general, the delay is lower in designs using smaller transistor length. presumably due to the shorter gate length. Next, power and energy analysis was also carried out on the designs. It was found that, the average energy consumption of these designs is measured over a clock period of 20 microseconds. The results are presented in the form of bar chart and line chart as shown here. So based on the result, there are three observations. Number one, transmission gate-based design consume less energy compared to past transistor-based design at 22 and 32 nanometer only. And then energy consumption is observed to be lower in MS2 configuration. And then number three, energy consumption is higher in a smaller transistor, despite lower voltage is used for smaller transistor. And this is counterintuitive. Right? So this third observation, where the energy consumption increases with smaller transistor length, can be explained by looking at the instantaneous power waveform of a few selected designs, as shown here. Right? The peak dynamic power actually decreases up to 3 times when the transistor length decreases, which follows the trend of lower voltage. Right? However, the static power increases up to several hundred times when the transistor length decreases. Therefore, it shows that the contribution of static leakage energy within the overall measurement of energy consumption increases with smaller transistor length. The parasitic effect of leakage power outweighs the power reduction benefit of reducing transistor length and operating voltage from 45 nanometer to 22 nanometer. Next, setup time analysis was also carried out on all the designs. Right? So the optimal setup time is the minimum amount of time required for input D to be stable before the clock edge to prevent output metastability. In simulation, the optimal setup time is taken as the minimum setup time required to prevent more than 1% increment of clock to Q delay from its nominal value. So based on the setup time analysis results here, right, the transmission gate-based designs result in more stable setup time characteristic curve, but it has no obvious benefit in reducing the optimum setup time. And also, there's no obvious correlation between transistor size and the optimum setup time, as shown in the result here. Next, hold time analysis was also carried out on the designs. The optimal hold time is the minimum amount of time required for input D to be stable after the clock edge to prevent output metastability. In simulation, the optimum hold time is defined as the minimum amount of time of hold time that is allowed without causing metastability, okay, of the clock to Q delay. So based on the hold time analysis as shown in figures here, it was noticed that transmission gate-based design have lower optimum hold time compared to past transistor-based design. And also, a general but not consistent trend is observed where hold time tends to decrease with smaller transistor length. Based on the result analysis, right, the optimal design of non-volatile flip-flop is selected to be RRTG-NV-DFF MS2 at 32 nanometer, with the reason that it's power saving and it is also and the timing performance is is good. Right. Comparing this design with CV-DFF 32 nanometer, it is 2 times lower and it consumes 1.373 times less energy. And then comparing with CVTG DFF 32 nanometer, it is 188 times slower and it consumes 3.87 times more energy. So the delay can be further optimized by using memristor with lower switching delay. And considering that the design can be powered down to achieve zero slip leakage energy, the energy consumption is still reasonable. And then energy consumption can also be further reduced by not updating the memristor branch every clock cycle by using compare and write mechanism. So finally, the design non-volatile flip-flops are used to construct simple sequential logic circuits to further verify their operations. For example, a mod 16 asynchronous counter was constructed. As shown in the timing diagram here, the counter can count from 0 to 7, where it is powered down. And then when power is restored, the counter can continue counting from 7 until 15, where the count cycle reset at 0. Besides, the design non-volatile flip-flops can also be used in the design of a mod 4 synchronous counter. As shown in the timing diagram, the counter can count from 0 to 3 and then repeats at 0 and continue counting. When it counted to number 2, it was powered down. The counter can resume counting at number 2 when the power is back up and continue counting at the next rising edge of the clock. In conclusion, it was found that the effect of static leakage power on total power consumption becomes more prominent as the transistor size scales down from 45 to 22 nanometer in both conventional and proposed design. This causes the power dissipation to be high, even when voltage level of the circuit is lower. It therefore justifies the need of designing a non-volatile D flip-flop for application that has long idle time to achieve zero slip leakage energy. And also, transmission gate is found to be effective in improving the timing performance of design, but it uses more components, right? And then master-slave 2 configuration introduced in this project was also shown to be effective in power reduction. All in all, it is important to note that it still requires a significant amount of research and experiment before the proposed designs can be implemented in real-life digital integrated circuits. Myristor-based non-volatile flip-flop is an interesting field of research which has the potential of revolutionizing the next generation SoC design, such as those used in IoT devices. Nevertheless, the use of this non-volatile D flip-flop is not limited to IoT devices, and it may become industry standard for low-power application in the future when the technology for integrating CMOS and myristor becomes mature. And here's the references. And thank you so much for listening